Okay, this is lesson 1.3, and we're going to look at radicals today. And we're going to make mixed and entire radicals. So you'll find out what that means, but that's the idea for today. What we're going to do, though, to get started is we have to be able to break a number down in this lesson into its prime factors. So each number is actually made of a unique set of prime numbers. And so we can do that in a number of ways. You probably saw this back in grade 8 and perhaps grade 10 when you were factoring, but I'll show you again here. And there's a couple of methods that I've seen students use over the years, so you can decide which method kind of works better for you. So the first method we'll use, and I'll show you, is called a factor tree. So basically in a factor tree, you're breaking up a number into things that divide nice and evenly into it. So for example, 15 is 3 times 5. So you just have to think of numbers. Okay, I know 5 goes evenly into 15. Oh yeah, 5 times 3 is 15. So you break it up, and it's called a tree because it kind of branches out. And you keep going, but you stop when you can't break up a number any further. So for example, 5 is a prime number. I can't break it up any further. I could do 5 and 1, but that's kind of redundant. So I stop. And same with 3. 3 can't go any further, and so I stop there. So now I've broken 15 into its prime numbers. So 15 is actually 3 times 5. Okay, and it's the only number that's equal to 3 times 5. 180, let's try that. I always tell students, if something ends in a 0, always break it into 10 first. So 180 is 10 times 18. And both of those numbers can go further. They can be broken up even more. So now let's look at the 10. 10 can be broken up into 5 and 2, since 5 times 2 is 10. And I have to stop there because both 5 and 2 can't go any further. They're both prime numbers. Let's look at 18. 18 is, you can do 6 times 3, or you can do 9 times 2. It actually doesn't matter how you break the number up. You'll always end up with the same endings at the end. So we'll do 9 and 2. 2 is a prime number, but 9 I can go further. 9 is 3 times 3, and now I can stop. So 180 actually has a bunch of prime numbers. And when you write it out, you want to write them in order from smallest to largest and group them together, because it's going to be easier today when we're working with grouped. So 2 and 2, 3 and 3, and then I have a 5. Okay, good. And so that's called a factor tree, kind of breaking it up and having these branches come down. There's another way that I call the ladder method, and I'll show you that here. And then you can decide if you like the ladder method better or if you like the factor tree method better. So I make a little ladder, and there's going to be some rungs to my ladder. You don't want to make too many rungs yet, because you kind of don't know how many there's going to be. But so just keep asking yourself, okay, what is a prime number that divides nice and evenly into 2,205? 2,205 happens to end in 5, so 5 is a good one to start with. So you want to divide by a prime number that you know goes nice and evenly. So, and when you divide by that number, you want to pull it out like that. So I put a 5 there, and then I divide 2,200 by 5. I'm going to use a calculator just in case. I don't know why I closed it there. Okay, there we go. Okay, so 2,205 divided by 5, 441. Okay. This number divides by 3. You can tell if something divides by 3 if you add up the digits. So 4 plus 4 plus 1 is 9. And 9 divides by 3, so this number is going to be divided by 3. You can also just test it. So 441 divided by 3, 147. And I'm going to keep going. So you always want to divide by prime numbers only, though. So I can divide by 3 again. I get 49, and you keep going as long as you can. 49, I know, divides by 7, and I get 7. You stop once you reach a prime that can't be divided any further. And these are all your primes. So those would be like the endings. If you made a factor tree, those yellow numbers I highlighted there would be the same numbers you would see at the ends of your factor tree. And again, I'm going to write them in order. So 3, 3, 5, 7, 7. 3, 3, 5, 7, 7. So that's the prime factorization of 2,205. Okay, so we're going to need to be able to do that throughout the lesson, kind of break a number up into what it's made out of, because we're going to be taking square roots of certain parts of that number. Okay, the second thing you need to know about this for this lesson is something called the multiplication property of radicals. So this is just at the bottom of the first page here. I'm going to highlight it. What this says is you can actually break a square root up. So for example, square root of 14, you can break it up. If you know 14 is 2 times 7, it's going to be the same as square root of 2 times square root of 7. This doesn't work for adding and subtracting, but it does work for multiplying. So I'm going to prove this to you on my calculator. I'm going to do square root of 14, and I'm going to do square root of 2, square root of 2 times square root of 7, and it should be the same number. Yep, look at that. So you can break up a number if you're doing a square root. You can break it up into different parts and answer them separately. Okay, so that's going to be key here. Okay, and that just says it here again, but more formally. Okay, so if you have two things multiplied, you can break it up into the two parts. Okay, so we are going to break up these radicals and write them as what's called a mixed radical. I'm going to show you the first one. I'll use this blank space up here because there's not too much space there. So I'm going to take this first one, negative root 75, and show you how to break it up into something called a mixed radical. So what that means is we're going to answer only part of the square root, and the other half we're going to leave inside the square root. And I'll explain why we want to do this too. So this is the number we're working with. I'm just using the space above it. Actually, I'll even go up here. Okay, so looking at this square root, I can't answer it exactly at the moment because 75 is not a perfect square. Nothing multiplied twice equals 75. But what I can do is look at what 75 is made out of and find its prime factorization. So I'm going to use the factor tree. 75 can be divided by 5, or let's divide it by 3. And you would get 25. And 25 is 5 times 5. Boop, boop, boop. Okay, so I should be able to write square root of 75 as, I'm just going to ignore that negative sign for now, 5 times 5 times 3. Okay, so what you want to do here is break up the square root into the two parts. I'm going to keep those 5s together, and then I'm going to keep the 3. Remember, we're allowed to do that because of this multiplication property of radicals. So I'm going to break this up into the 5s and just leave the 3 alone like that. Okay, square root of 5 times 5, 5 times 5 is 25, square root of 25 is 5. So when you have a pair of numbers like that, when you take the square root of it, it equals just one of those numbers. So the square root of 25 is 5, so I can actually answer that part. So that's the idea here, is part of the square root can be evaluated. So this would equal to negative 5, and then the root 3 is not a perfect square, and so that can be. The reason we like to do this is because it makes the numbers a lot smaller. And so in larger problems where we are dealing with square roots, if you've been worked with smaller numbers, it's often more ideal. You can simplify things and keep the numbers small. It's kind of the same reason we want to like simplify fractions. Larger numbers are more difficult to work with, so doing this kind of makes the numbers smaller. So in the end, we have negative square root of 75 equals negative 5 square root 3. Those are the same number. I'm going to show you. So negative 75 is this lovely decimal there, and negative 5 square root 3 should be the exact same number. So the nice thing is if you've got a calculator by your side when you're doing these questions, you can always double check at the end. Your answer should match the original radical. If it doesn't, there's something that's gone wrong with your your work there. Okay, so again, break the number into its parts and separate it. And if there's any pairs, you're going to be able to evaluate those exactly. And then any numbers kind of by themselves, you have to leave them alone in the square root. So that's called a mixed radical, where you've answered only half of it and left the other half. If you're feeling pretty confident, you could pause here and try the other two on your own. If not, then you can keep going with me. Okay, let's do 42. I'm going to try and squeeze it in here. The next one says root 42, right? Yeah. So 42, I'll do the ladder method for this one. I know I can divide that by 2. It would make 21. 21 I can divide by 3, and that makes 7. And I can't go any further. So root 42 is 2 times 3 times 7. None of those numbers are pairs, and so it doesn't make sense to break this radical up because you're not, like, there's no pairs that you could answer. So this one cannot be written as a mixed radical. You can't simplify that radical down to smaller numbers. Root 42 is the only way to write that radical. Okay, let's try the last one. The last one's going to be a cube root. So again, you can pause here if you want to try it on your own. We've got 54, so I'm going to make a factor tree. I know 54 is 9 times 6. 9 is 3 and 3. I'm going fast through the factor tree now because I'm assuming that we all understand how to make one. Yes, okay. So cube root of 54. So I'm going to break up 54 into its parts. I notice I've got 3 3s and a 2. Okay, and I'm doing a cube root here. So these triple 3s, I'm going to separate them out. And I'm going to keep the 2. Okay, so those two are equal. Now 3 times 3 times 3 is 27, and 27 is a perfect cube. So I can evaluate that. It equals 3. Cube root of 27 is 3. So the answer to that part is 3. I can't answer cube root of 2. It's going to be a messy decimal, so I'm going to leave it as cube root of 2. But now I have simplified this down to its mixed radical form. So when you're making mixed radicals, if you're doing a square root, you want to look for, when you're separating it into its prime numbers, you're looking for pairs, because pairs you can evaluate. And then when you're doing a cube root, you want to look for these triples, because triples you'll be able to evaluate as well. Okay. And at the end, if you would like to, you can double check your work. That's the nice thing about this section, is you can always do that. You can do 54, and that should be identical to 3 math. Yep, they're the same. Okay. All right. Next group of numbers. Write each entire radical as a mixed radical. So example 1, we use this property of splitting it up into its prime number factorization. That's one strategy for doing this. There's actually another strategy as well, and you can use whatever strategy you feel more comfortable with. So after I show you example 2, you can kind of decide, do I like example 1 or do I like example 2, and then just continue with that strategy. If you are very comfortable with the perfect square and perfect cube numbers, you will like this next strategy. If you have trouble memorizing them and recognizing them quickly, you'll probably find this next strategy a little bit more challenging. Okay, so it just kind of depends on the student. So example 2. So the other way to do it is to break up the numbers. So let's look at 63 first. I'm going to use the space up here. And I know I have to take the square root. So I'm going to try and think of how I can break up 63 where one of the numbers is a perfect square. So for example, 63 is 10 times 7. I just happen to know that. So to do this method, you have to have really good number sense and really good multiplication table skills. And 9 happens to be a perfect square, and I know how to evaluate the square root of that. Okay, so I can break that up into square root of 9 times square root of 7, and I can evaluate this one. Square root of 7 we can't evaluate, so we're going to leave it. So it would be 3 root 7. This is a fast. You're really fluent with your multiplication skills and your square, perfect squares, as I mentioned. But yeah, it's not for everyone. So let's do B. You can also pause here and try these on your own. So this one we're doing negative cube root 80. So if I'm thinking of the perfect cubes, so we're doing cube roots, so we got to think of perfect cubes. I know my main perfect cubes are that are less than 100 are 8, 27, and 64. So 8, this one divides nicely into 8, so I can break this up into 8 times 10, right? And 8 is a perfect cube, so perfect. So this is the same as negative cube root 8 times cube root 10. And I'm going to evaluate the cube root 8. So that would be 2, and I'll still have the cube root 10 there. Okay, so this method again is faster if you are quite fluent in your multiplication tables. Okay, and last one, 4th root of 243. So 4th roots, we need something that multiplies I know that 81 is a perfect 4th. Sorry, my Wi-Fi is gone. Okay, there we go. So I'm going to break this up into 81, 243 divided by 81. So I'm going to break this up into 4th root of 81 times 3. Yeah. And 81 actually has a perfect 4th root is 3. So 3 times 3 times 3 times 3 is 81. So this would work out to be 3 4th root of 3. And there we go. Okay. So that's how you do those. And again, you can use either method. You don't have to use the one I just did there to do the questions. Okay, now we're going to go backwards. What if you have a mixed radical and you want to change it back into an entire radical where everything is under the square root of the cube root? So that's what we're going to do here. Okay. So start with a 6 root 5. 2 ways to do it. First way is to just think of, so I want to get everything underneath the square root. So what I want to do is take this, put it underneath the square root, and the answer would be equivalent to 6. So one way of doing this is to think, okay, what number, when I take its square root, it equals 6? Well, that number is 36. Okay, so I've just replaced the 6 with the root 36, and then I can put these together under one roof. So 36 times 5 is 180. And again, you can always double check here. I don't know why that goes blank. Always double check by doing square root of 180. And that should match 6 square root 5. Yep, match. So remember when we took the 6 out, it would have been a double. So it would have been 6 times 6 times 5. You would have had 2 6s to make the 6. And then all those numbers multiplied together is 180. So whatever way you feel more comfortable with, you'll still get the same answer. Okay, and then for B, if you want to pause and try yourself, you can. 5 cube root of 10. So this is the mixed radical into a cube root. I want to replace the 5 with a cube root that I know. So 5 is cube root of 125. That is 5. That I've written it as a cube root, I can combine it with the cube root. That would be 1250, and I'm done. And again, you could check on your calculator that those are equivalent. Okay, last one. So a fourth root that equals 2 would be 16, since 2 times 2 times 2 times 2 is 16. So the fourth root of 16 is 2. So I want to make this 2 into a fourth root of 16. Multiply 4 2's together, basically. And I'm going to combine it with the 5. Sorry, my 4's are a little wonky today. 16 times 5, I believe, is 80. Yep. There we go. So that's how to change a mixed radical into an entire radical. And that is the end of the lesson. So basically the idea today is, can you change, the first kind of skill was going from an entire radical into a mixed radical, where you evaluate just part of it. There's 2 methods to do that, and you can use either method. And then you were going backwards and changing a mixed radical into an entire radical. So I'll pause the video there.